the whole world at our feet, watching seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand, open arms. This is home where we are, ever strong in the world that we made. I still hear you in the breeze, see your shadows in the trees, holding on, memories never change.
Okay, now you should be able to hear me. This is why I usually wait for the feedback from YouTube, because otherwise, yeah, you might not be able to hear me. So, again, welcome everyone, and yeah, let's welcome also my moderator today. That is Foxtrot Charlie. His nickname is right here. So, if you have any questions during the stream, do ask Foxtrot Charlie, and he's going to magically, well, telepathically actually, let me know that there is a question and the question itself, so I can answer it. Apart from that, if you are on our IRC channel, then, you know, on Freenode, then !Q and then the question, that also works. Okay, so today's topic is going to be Google's CTF qualification round of 2018. Actually, 3 tasks from that. I'm not sure if I'm going to be able to do all 3 today, because, well, these are, well, 2 a little more, 1 easy, 1 medium, and 1 hard challenge, basically. Yeah. So I might be able to go through all of them today. If not, that will overflow into next week, and I will next week finish the topic. Otherwise, yeah. I guess I'm going to start the stream, that main topic, as usually, around 15 minutes past. So before we get there, I'll do, yeah, the usual stuff, which is show you some web pages and tell you some news and answer some of your questions. And then around 15 minutes past, where everyone who is late actually arrives, we can get going with the main topic. Perfect, so let's switch here and here, and we'll get to that second page in a second. This is Foxtrot Charlie's website, segmentationfall.github.io, so be sure to visit it. And I'm pretty sure he updated the post. No, he didn't. But I'm pretty sure he wants to, so do visit his website. And I guess I'm going to give you links on the chats. Here we go, and here we go. Okay, perfect. Apart from that, Guest created a short quiz for you. And I guess, yeah, I guess Foxtrot already gave you the link on chats, but in case you missed it, here we go again. I'm going to give you the same link. You do not have to transcribe this unless you really, really want to. And there are a couple of easy questions about today's topics. You can answer them, and then yeah, I'm not sure if it actually shows you the correct solutions, but I should be able to see at the end of the stream how many people correctly answered the questions. That's assuming I actually do know the correct answers to these questions, which I am not fully sure. Cool. Next, and this is really important. Live Overflow got this. This is an award which you get from YouTube if your channel exceeds 100,000 subscribers, and there are some other also requirements. And Live Overflow got it, so congratulations to him. Be sure to congratulate Live Overflow on Twitter. It's at Live Overflow, like twitter.com/Live Overflow. As far as I know, his channel is the first deeply technical security channel which ever surpassed 100,000 subscribers on YouTube. So that's actually really amazing and really well done. If you do not know Live Overflow's videos, do check them out. He does, I think, some live streaming, but he mostly does videos, shorter videos in like 10-15 minutes about a given topic, which are really amazing, really well done, and really well edited. So be sure to subscribe, and let's basically keep it going. So congrats to Live Overflow for getting the magical silver button on YouTube. I'm really happy about it. Apart from that, so staying in the topic of today's video, some challenges for Google CTF qualification round 2018 were open sourced. You can go to Google's GitHub. In this case, that would be github.com/google/google-ctf, and and there we will have beginners and qualification tasks. Not all tasks are there, but most of them. They might appear again in a few days, like the missing ones, right? Okay, and we have the tasks which we will be doing today. So that would be better zip, wired CSV, and basics. So if you want to take a look how the task was actually done from the inside, how the source code of a task which you had to reverse engineer looks, then do check it out. I guess I should give you the link to this as well. And warning, spoilers, obviously. So there are spoilers in that directory. I will keep this open. Let's close this one. And this is the website for today's challenges. I did already talk about the CTF last week. If you didn't watch last week's live stream, it was Tuesday actually, then I did the whole beginner's quest and like all the challenges were, and it took 3.5 hours, so it was a longer stream than usual. Today I'm not going to do all the challenges in the main qualification round because the beginner quest wasn't, it was for fun. It was purely for fun for people to start with CTFing. Now the challenges were to pick the 10 best teams in the world, so they were much harder in case what you had to do. There were 5 tasks in each category of crypto, MISC, Pwn, reversing, and web. And I did create 3 of these tasks. I created better zip, as mentioned, wired, and as mentioned, crypto, better zip, MISC, wired, and reverse engineering back to basics. So these will be the tasks which I will talk about today. I guess, I guess we still have 8 minutes to kill, so if you have any questions, do let me know. Apart from that, I'm thinking of from which task I should start. I will start either with wired CSV. I'm probably going to start with wired CSV because this is the simplest tasks to start, so it should be quite easy to solve it. Let's see if there are any questions from you. If yes, then I will answer them, and in a couple of minutes we will start the topic. Cool. So there's one question. Let's see if I can actually show it to you. It should appear there. Let's see if it does. It does. Perfect. How can I get info about process memory on Windows? I mean about something like Linux /proc/pid/maps file. It's a good question. You can use, if you're speaking about how to do it programmatically, you can use, I'm going to show you, I guess, the name of the API. It's called Virtual Query or Virtual Query EX. msdn virtual query ex. That's for another process, to get the information about another process. Otherwise you can get the information about your process without the ex here, because here you can pass the handle to another process, which you of course need to have opened first using, I think it was called open process. And basically the way it works is that you can start enumerating from the beginning, and it gives you information about regions which are allocated and regions which are not allocated. So you start like with 0 and it will tell you it's not allocated. So this like memory basic information will say, yeah, it's not allocated. But it will also tell you what's the size of a region, so you will know that, oh, this is the amount of memory from the beginning which is not allocated, but then starts something which is allocated, so you query again and check what is allocated, and so on and so forth. Now there is actually from sysinternals a really cool tool to see the map. All the debuggers can basically display the map of a memory, but there's also a cool tool from sysinternals. It's called VM something, VM map, I believe. Yeah, VM map. And the way it works is like you select a process and then you can see basically the map of the process. So yeah, the address, the type, and so on, and the protection. So basically everything you have in proc bit maps will be displayed here. That being said, there is no sudo file on Windows which can do the same. You do need a specialized tool to do it. If you have a debugger, then the debugger usually can display you, show you the memory map of a process. So yeah, I guess I can give you links to both this and this. Here we go. Cool. Actually, if you go to my GitHub, which was, I don't know, github/Gunveil or something like that, there should be some source code you could analyze which basically dumps the memory of a process. So yeah, repositories, and that was called oh yeah, this one, Hyperjob. It's not popular. Just another tool for dump the process memory, and virtual query. Yeah, virtual query is also somewhere used here. Yeah. Here we go. So you can take a look how it works. I guess I can give you a link to this as well. That being said, I did not test this code recently. This code was written a couple of years ago on Windows 7, and it did work. Yeah, like 6 years ago. Whoa, time flies when you're having fun. So yeah, but you can take a look. Have you hacked your lights on the wall yet? No, and this is exactly why this light here, the Aurora leaf, is off, because my wife isn't home today, and she usually sets up the lighting for my the lighting for my live streams. And yeah, so since I still haven't had time to take a look at it, I didn't hack it yet. Therefore, I do not have access to the light. I can turn on the light, I can turn off the light, but I cannot select the proper profile for the light. So, Internet of Things, but I do need to take a look at it. So yeah, that was the answer. Why does Linux save those information on the proc? Does it generate when someone reads it, or is it always there? Because it can hurt the performance. So it's like this. Proc is actually a special file system. If you open, and let's do just that. Let's see if, I didn't check if my Linux console works. Does it work? Does it work? Yeah, it works. Perfect. Here we go. So if you type mount, and I have quite a lot of, since this is a VM, I have quite a lot of partitions here. But there is something called proc file system. Okay, I have quite a lot of stuff. Here we go, proc. And proc is a special file system which is provided by the kernel. So these aren't real files. This is something which is backed by a piece of a kernel, where the kernel doesn't create these files. It actually creates the file once the file is opened and the information is requested. So even though we can list that, these files exist and they have a certain size, that's not really true. Some of the content is created when the file is opened and when the information is actually retrieved. So it doesn't hurt any the performance because yeah, it doesn't generate that information until the information is being requested. So I guess like if we do proc self like list it, you can see that most of the files have size 0 and the 0 isn't true, right? It's just that while listing the directory, it doesn't really it doesn't really know the size of the content because the content is not yet generated. But if we do like cat proc self map, then we can see that there is actually some content, even though if we do stat on it, it says that, yeah, that the size is 0, which clearly isn't the case. Again, because this isn't a real file, this is only something that is generated on request. Okay, one more question, since we have one more minute. Any ideas how to set up firewall, like IP tables? That's network security, that's not really my area. All I can say is, yeah, set it up correctly. Yeah, do ask that question to somebody who is actually into network security, because they will be able to give you a proper answer. How did you start with security stuff and CTFs? So with CTFs, I started actually with war games and not CTFs. I started with war games because someone on IRC threw a link to a 3-level war game, and on another IRC channel then a link to a 7-level war game, or 8-level actually. Most of that was in JavaScript actually, and like really old Internet Explorer 4 or 5 JavaScript, that kind of JavaScript. And yeah, so basically I started with war games, and that was my give or take first attempt at security. And after that, yeah, I basically tried to solve all the hack me's and war games which were available. I did start in CTFs. There was in my country something called Security Days, and that was actually what we would now call an individual CTF, as in you start by yourself but without a team, and there was a qualification round, and after the qualification round, I think 5 best people or 10 best people were brought on site to play in the finals, and the first time I got the 2nd place, and then I won, I think, the 2 next competitions. That was pretty fun. Yeah, like actually that was ages ago, that was, I don't know, 12 years ago, when I looked up the like the people who participated, there were a lot of people who then ended up in Dragon Sector. So yeah, it seems they started around the same time. And from a professional point of view, I did start in security also because someone on IRC said that the local antivirus company is looking for folks to do reverse engineering of packers and creating static anti-unpackers, and that's basically how I got professionally into security. So yeah, and the first CTF, that was a team CTF I actually took part in, was in 2008, I think, on a confidential local CTF. I didn't know CTF time existed. I don't think CTF time existed at that time anyway. Yeah, basically when I noticed that there is something called ctftime.org, and it's actually like an aggregate and a ranking for all the CTFs, I said, yeah, we're creating a team and we're going to basically win that ranking, which we did, by the way, so I was also happy with that. Yeah, if you look now on CTF time, Dragon Sector is top 1. But the season isn't over yet. Let's see what happens. There is still 6 months of CTFing left. Okay, so let's stop it here, and let's... there are a couple of more questions, but we will get to them when we have a break between the tasks, I guess. And let's start today's topic, which again is the Google CTF qualification tasks, the tasks which I did create. So I am familiar with them from both, I guess, testing perspective and both a creator's perspective. And we will start with this one, which is MISC wired CSV. I guess I can give you a link here and a link here. So yeah, this was a task which in the end was solved by quite a lot of teams, I guess. How many teams? Oh, it's not written here. It was written somewhere. Here we go, 42 solves. So I think like around 300 teams participated and solved anything. Let me see the scoreboard. Sorry, the teams. Oh, it doesn't display all the teams, just the first 100. Well, okay. But I think there's around 220 or 300, something like that, something in that range, teams which actually solved something. So 42 teams out of 200 who solved anything did solve this task, so it was one of the easier tasks. As you can see by the dynamic scoring, in the end the score was assigned 220 in comparison to, for example, this one, which had 5 solves and was worth 420. So it was in the easier bucket, but it wasn't super easy. Cool, so we can download it and we can extract it. You basically get 2 files. I should be able to show you it. Here we go. Yeah, you get 2 files, which is wires, a photo, and a 7-zip file. We can extract the 7-zip file into data, and once it's still extracting, I can read this. We have a photo and a CSV file. CSV stands for comma separated value, as you probably know, so it's basically like super simple serialization of data. Note, the flag does not follow the CTF format, but is clearly marked as the flag. Please add the CTF, this with the brackets around the flag manually when submitting. Now, why is this? That will be explained in a few seconds, because this actually makes sense when you start to think about it. Okay, and I guess we can take a look at the photo now. Dear photo, where are you? Here we go. No, you cannot see the photo. Now you can see the photo. Okay, so this is the photo. The photo, as you can see, is some device, and actually 2 devices. There is one device here and another device here. Here we can see that there are some probes connected to this chip, whatever it is, on some motherboard. And then we have a second device, because all the wires actually go to this, and it has a name like SALEAE. Now, if you're into electronics at least a little, you know that this is what's called a logic analyzer, which basically is a device which you hook up to a chip, assuming, let's assume that the chip is actually a digital chip, so it, has outputs of 0s and 1s on the pins. And what it does, it records the state of a pin. Is it a 0 or is it a 1? Or like the other way around, right? Depending on how the logic works here. So yeah, basically the task is probably will be related to the data which was logged or recorded from these pins, maybe these pins as well, by this device, and was dumped into a CSV file. We'll get to what is this device in a second, and the CSV file looks like this. I guess I'm going to do. So yeah, it's just a bunch of numbers, but at the top you do have the names of the columns, which is time in seconds, then wire 6 analog, wire 7 analog, then time in seconds again for some reason, wire 0 digital, time again, wire 1 digital, and so on and so forth, until we reach wire 7 digital in the end. But as you can see, there are not too many samples here, which is kind of weird, but I'll explain it in a second. Yeah. So this is what you get, and now you have to start thinking, okay, what is it? Now, the way I thought the players will go around it, and that's actually what happened after reading a couple of write-ups, is that I assumed the player will start with figure out what is this chip here, this C012294B-01. And that's actually something which is called a POKey. That's not how you type. POKey. POKey stands for, I think, potentiometer or pot and keyboard. And the other giveaway, somewhere here on the photo, let's see if I can find it. It's not super visible, but that doesn't matter. it does say Atari here, so this is an Atari motherboard. Actually, if you look for Pokies were basically used only in Atari, so this is a giveaway. Then you do have some other chip here, which you can take a look, what is it, and some other chip here. And it turns out that this is actually an Atari motherboard, and it's actually an Atari 800XL motherboard at that. So yeah, it's Atari 800XL. If you don't know what's that, that's okay. It's actually an 8-bit computer from the 80s, and it was my first computer actually, and is lying right next to me, the exact motherboard, because I still didn't clean my setup after I did this recording of a signal. Now it is a little modified from what you would normally find. For example, usually there are chips here. There is the I think the memory controller and the ROM, which contains the basic interpreter, or like the BIOS and other stuff here. BIOS is a big word, it didn't have a real BIOS. And usually it doesn't have a white board here, which is, what is it? I think that's the, that's actually the additional graphics card. And it doesn't have wires going here because this is actually a RAM extension, like together with these two things. So yeah, but you could figure out it's actually an Atari. So what you do, you basically look up on Wikipedia, okay, so what is this chipboard, how does it work? And it turns out, after you do that, and we can, I guess we can do that. Atari Poki. Here we go. Yeah, it's not like hard to find information about 8-bit computers, especially the popular ones. Basically, what you find here is that the chips where the probes from the logic analyzer are connected are these ones. Yeah, exactly these. There's also another one which is VSS, which is ground. It's where the two probes are connected, but that doesn't matter. We can ignore it. It's just so the logic analyzer knows what's the ground level and can, well, derivate that. Anything which is higher than the ground level is probably a 1. Okay, so yeah, just looking at this, we can see that this is handling the keyboard. So probably what you should be able to figure out by now is that somebody was typing on the keyboard and the logic analyzer recorded the signal which that chip received from the keyboard, or did it receive the signal from the keyboard? How does it work? We don't know yet. Yeah, and yeah, but the flag is probably in that signal, and it was probably typed into the keyboard. That's the idea behind this task. So now what we have to do is we have to figure out which pin is which, but that's rather easy because I didn't do anything funny with naming them. Well, I did a little funny. Okay, so it's like this. Here, the columns are named by, wire, but by which wire is it, right? And here, if you look at the picture, you'd have to find the documentation of this device and figure out, okay, so which wire is which wire is number 1, which wire is number 0, and so on, which wire is number 5. Do we start at 0? No, yeah, we start at 0, basically. Okay, where's my mouse? Here we go. So just to speed it up a little, this wire here, the the black one here, which goes here, and goes here, this is the 0th one. Then we have the brown one, which is wire number 1, the brown one. Then we have the red one, which is 2. I have absolutely no idea how to name this color one. Let's say light red, which isn't accurate. Yeah, this is the 3rd one. And then we have yellow, green, blue, which goes there, and I guess violet. That being said, we also see some black wires at the bottom, and the black wires are just ground, and most of them are not connected anywhere. The ones which are connected here, so we can ignore it. This is just ground level. So yeah, we see that the first, like the 0, wire number 0, the black one, goes here. You can actually trace it, like all the wires, so if you don't see color, that should be still fine. goes to this pin, then the brown one, which was the wire number 1, goes here, and the red one, which was wire number 2, goes here. So these 3 pins are 0, 1, and 2. So if we look again at Wikipedia, we see that, oh, this is K0, K1, and K2. And do notice that some of these have a line above them. That means that actually the logic is inverted. So I think 0 will be high and 1 will be low, like 1 will be ground. That being said, for some reason, Wikipedia has an error, and I also saw this error in some schematics. This is wrong. It should be here as well. The line should be here as well. All of them are inverted. So I don't know why Wikipedia has this error, but it doesn't matter. Some of the schematics you can find online are okay. I have this correct and have the line everywhere. So yeah. We can color it orange, but on my screen it isn't orange, but let's call it orange, okay. So yeah, if you then look at the bottom row, then we get the orange one here, then the yellow one, and then the green one. So again, this is 3rd, 4th, and 5th. So basically, wire 0 maps to K0, wire 1 to K1, wire 2 to K2. I wasn't trying to be annoying here with the wires. Now, the other 2 wires, which is the blue one going here and the violet one, which is goes here, are connected to this and this pin. I guess the violet one is the bottom one, so the violet one is connected to KR2, whatever that is, and the other one to KR1. So yeah, what are these? The first 6 probes or pins, if you will, are the keyboard scan output, whatever that is. We don't know yet what is that. And the KR1 and KR2 are the keyboard row stroke input. So that tells us something. The word output here means that the signal is sent on these pins, and the input means here that the signal is received on these pins, which is something. Now, what we would read about, and what is obvious when we start looking at the schematics in a second, is that the way it works, it's basically connected directly to the keyboard matrix, like to the matrix with all the keys, right? And the 6 pins are being used to do a scan of the matrix, and the other ones are used to basically get the information of the result of a scan. And it's actually quite easy, but let's go to the schematics. I do need to find them. Please give me a second. I'm going to use the schematics which I am familiar with. You can find them on the internet pretty easy. I'm pretty sure that most of the team actually found these, or you can use some other schematics, like for example the datasheets for the Pocky, for the chip. Cool, so I think it's somewhere here. Okay. Yeah, I'm wondering if it's in my project directory. Because it's actually all the setup is related to my project, but I will tell you about that in a second. Or is it in my documentation directory? But it's in my documentation directory. Okay, here we go. These are the schematics. The schematics are actually, I think, reverse engineered or created by Mr. Jerzy Sobola. Thank you for doing that. The schematics are amazing. They have some minor errors, but they are amazing nonetheless. And let's find the right one. No. Yes, this is the Pocky chip. This is where our probes are connected, like these and these. And if you start looking at where does the signal go, it goes to these like 4051 chips, whatever these are. Like there is one here, and there is one here, and then there is some like register array, or like whatever, we don't care. And it goes into the input somewhere on another page, and the output somewhere. Do not pay too much attention to the input and output. That's yeah, that's complicated, but we'll get to that. Oh, or actually do pay attention. That's actually important. Okay, so this is one page which we need. Now this is the keyboard matrix, but before we get there, here is the keyboard connector on the board. So actually, if you look at this picture, this is the keyboard connection here. It doesn't look like the one which is on the normal Atari. I'll explain why in a second, but this is basically where the keyboard connector is, and it goes somewhere, usually to the keyboard. In this case, it doesn't go to a keyboard because my Atari is modified, but usually it would go to the keyboard. And the keyboard, as you saw, this is the keyboard matrix. So if we look at the numbers on the pins here, so like 1, 2, 3, 4, 5, 6, 7, and 8, you can actually find the same numbers here. So yeah, the way it works is basically it selects one of the rows. This is why it's called scanning, by the way. It selects one of the rows and then it selects the second one and so on. So let's assume this one is selected. And then it checks if, for example, on line 14, on column 14, there is a connection. If there is a connection, then based on the schematics, the signal will go to 0, to ground. If there is no connection due to some pull-up registers on the schematics, the signal will stay at 1 as high. So the connection is actually pressing a key. You press a key and you connect these two, like you connect the line with the row. If you let go of a key, then the connection is broken, and again the signal goes up. So you press the key and the signal goes down. Because of the connection, you let go of the key, the signal goes up. And it basically starts with like scanning this row. It doesn't matter, the order doesn't matter. The order is different than what I'm explaining. I'm just basically explaining the concept. It's with this row, and it checks are there any connections on this line, 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 and on this line. When it goes through all the 8 ones, is it 8? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, give or take. It doesn't scan this one. Yeah, that's a different mechanism, I think. Then it scans the next one, and again checks this line, this line, this line, this line, and so on for connection. So it's basically scanning the keyboard matrix, and it's doing it a lot. I think like several times per second. I don't remember exactly. I think it's around 64 times per second. The whole keyboard 64 times per second or something close to that. So yeah, that's basically the idea. It's pretty simple. Now, how we have like 8 connections here, right? But we had only 3 probes for input and out for the scan. 3 probes for input and 3 probes for output. What's up with that? And this is where we go back to these chips. What are these chips? These chips are actually so-called multiplexers. Multiplexer is a super simple device where you here basically give a binary number. Like let's say the number is going to be 101. A binary, right? 101 means it's 5 in decimal. And then it means select the line number, sorry, the pin number 5, like X5 on the other side. So this one, yeah, this one, and connect it to X. So basically you tell it here to which pin the X here should be connected. And therefore, if you look at the output, which we will do by the way in a second, of the probes, it turns out that it's going 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, and so on. So it basically selects, sorry, I'm going to make the zoom a little less. Yeah, so it selects 0 and connects it to X, then it selects 1 and connects it to X, and disconnects the previous one, obviously. Then selects 2 and connects it to X, and so on and so on. Now, let's trace where the X actually goes. And if we look at the X, it goes to KR1. So that's basically our input in this case. We would, in KR1, we would get notified, we would get 0 in case a key was pressed while the multiplexers were in a given state. And this is one multiplexer, this is the other one. and both of them are going 0, 1, 2. This is actually like you can think of both multiplexers as one chip, which takes a 6-bit input, and because we have, from K0 to K5, it takes a 6-bit input, and it gets 2 outputs. But let's ignore KR2, it only is for shift, if the shift is pressed, but that doesn't matter in this task. Let's focus on KR1. Basically, you select a number, a 6-bit number like 25, and if the key number 25 is being pressed, then we are informed by the changing state in the KR1. So this is basically all the all of the electronics there is. This is like not complicated, even I could understand it, and I'm totally a noob in electronics. Cool. So this is the moment where we can, I guess, take a look at how the signal looks like because okay, again, I don't have too much experience in solving hardware tasks. I solved, I don't know, 2, including this one, in all my CTF career. We have a person like K3K, KrzaQ, who in Dragon Sector, and some other folks as well who are like, yeah, like hardware, give me it 5 minutes solved. And I would be struggling with 2 hours with such things. But one thing I learned is that if you have a signal, then you need to look at it. Like, visually inspect it. Looking at these numbers tells you nothing. It tells me nothing. I don't know what this is. There is the time, and we can see that it changes, but how does this look like? Now, to do this, you actually need to somehow decode this, and I am not going to write that decoding. I am going to cheat a little. I'm going to use the signal which I have from the recording, but you can do it with a couple of easy Python scripts which just manipulate data. I'm going to tell you though how to read this file, because it took me 15 minutes after dumping the traffic to figure out what's what. So you can, if looking at the analog signal, and you do not have to, like the 3 columns here, the first one is the time in seconds. So as you can see, it grabs quite a lot of samples per second. The logic analyzer, I think it operated at 1 megahertz or something like that, like 1 million samples per second. That's the proper way to say it. And this is the voltage. So this is high. This is like near 5 volts. And 5 volts in Atari is actually 1, so assume this is 1. And if it would change to 0, then yeah. But this is how you interpret the first 3 columns. It's just the time and the voltage. Now, for the sake of this task, I gave the analog columns only in case the digital ones are not enough. And the digital ones should be enough. The signal quality was decent. There were some noise, but it was pretty decent anyway. So, how do you interpret the digital signal, and why? If you analyze the analog signal, you would find out that there's, I think, around 20 seconds of recording here. So why for digital wire number 7 you have only like 10 samples? What's up with that? And the idea here is that actually they are pretty smart about the way they store the data. They actually compress it, as in they do not store for digital data 1, 1, 1, 1, 1, 0, 0, 0. They only store when it changed. It flipped from 1 to 0 or from 0 to 1. So at the beginning they say it was 1, and then at 2 seconds and like this amount of, I don't know, even nanoseconds, I guess, or whatever, I'm not going to count the zeros. At this time, to 2.5 seconds, blah blah blah, it changed to 0, to then after like 5 milliseconds changed to 1 again, and then after 40 or 35 more milliseconds, it actually changed to 0 again, and then it changed to 1. So it's compressed like this. And so it seems that wire 7, which again was connected to KR2, which I said we can ignore because that's just the shift key, it changed only then. So you should read like all of these ones the same, like, sorry, no, not here. It's like here is the second colon and here as well. So like in pairs, and then decode them, you can decode them and have it at the best way to do it, and what we will probably have to do it in a second, is to decode it in a way that you store it in a structure and have a function where you can ask the question at this time, like 3 seconds and like, or exactly 3 seconds, what was the state? And it should do a binary search, for example, and say, oh yeah, at this time it was like 1. And because we will need to ask these kind of questions. Now let's look how the signal actually looked like. And for that, I am going to show you the original recording in the original software. If I find it. Okay, yeah, here we go. So it's opening. And again, you do not need this. You can easily use any other thing which can draw charts. And yeah, this is just because I don't want to type it now. So we have, we have the wires here. This is the scanning. So this is basically selecting the binary data. And this is the input, the result of the scan. And you can plainly see that the signal is usually high, but suddenly it drops to low, and it drops to low, and it drops to low. And this is totally 10 seconds, 20 seconds of recording. So 10 seconds is here, and then it's 20. So we can zoom in. And if you zoom in, you see that this is, as I said, basically changing from, like, this is 0, 1, 0, 1, 0, 1, the least significant bit of the selector for the multiplexers. Yeah, and this is like slowly changing and so on. This is basically how counting from 0 to 63 looks like in signal, in binary. One register changing really fast and then slower, 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 and slower. So if you see this kind of signal, you should know that this is just counting in binary. And okay, so let's zoom out. And now let's zoom in at one of these events. Let's call them events. And what you can see is that suddenly, when this was the number, the signal went down. That means that during this scan, it was detected that somebody is holding the key down. And the key was, because then, you know, the next key was being scanned and so on, so the signal went up again. But you can see here that the signal at the same number is actually still being held. And it's being held for some time. Because, you know, when you type, you're not like super fast, like you're not like lightning fast. So you push down and then you go up, but usually a couple of milliseconds did go through. So yeah, in this case, you can see that something was pressed. Now, the question is which key was actually pressed? And let's do one key, just looking at this, and then let's write a script for this. So first is we need to figure out what's the selector for the multiplexers, right? Okay, so I'm going to create a file for nodes to do just that. By the way, you could do it in this software as well, or like the open source equivalent of this software. You could actually tell it, yeah, treat this as a binary number and show it, but I'll do it manually, mostly because I do not know how to do it in this software. I just know you can do it. Yeah, I said I'm a noob in electronics, right? Cool. So, okay, we do need to basically know what are the states of these, like what's the number in these at the moment of the event. So this is the moment of the event here. Cool. So we have low at K0. So this is low. then we have high at K1, high, low at K2, at K3 we have low, and then here we have K4, this is low as well, and this is low, so we have low, low, low. Now I think that, well, you should remember that there was this inversion, so we should treat low as ones, I guess. If this doesn't work, we can always backtrack, and high as zeros, so this is the binary number. And, well, it's quite easy to interpret because there is no ambiguity here. It is 5 for the first one and 7 for the other one. Like this number is 5 in binary and this number is 7. So let's look at the schematics again and try to look which exactly row and line were scanned during this time. To do that, we go here, and we know that here we actually have 5 selected. Okay, so 5 is selected, 5 goes here, here, here into input 5. So this is just like this, input 5, and this is, we had 7 here, so 7 goes here, which is output 7, which is cool, nothing changes here, but here, input 5 goes to, 14. So 5 goes to actually pin number 14, and 7 goes to 5. 5. Okay. So if we go here and we look for 14 and 5. So 14 is here. Now 5 is here. And I'm pretty sure this is not correct. So the other interpretation of it was actually 0, 1, 0 and 0, 0, 0. Which would be 0. If you write an application, you know, which is just flipping the flag. And here is 2. So let's try it this way. Let's go back here. Actually, no, let's go back here. And we have 2. Input 2 goes to 12 and 0 goes to 6. So 12 and 6. Let's see if this is correct. Okay. So this is 12. This is, no, it's, I mixed something up. It's, sorry, again. No, it goes to 12. What am I missing? Because, yeah, if you look here, right, 12 and 6 actually give you G. And I know for a fact that the first letter is F, because the first word is flag. So I'm mixing something up. Let's see the signal again. Okay, so we have low, high, low, 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 and low. So this looks okay. Let's go and look here again. This goes to input 0, 2 goes to 2. Yeah, there is no numeration change here, which is fine. And here, yeah, I would expect actually, oh, maybe, yeah, we had this okay, I think, with 7, with the previous interpretation. So this was okay with this one, 7, which means that this should be the same, but it didn't look like it's the same. I'm mixing something up. Maybe that's not the first character after all. Maybe that's the... So, okay, what we did get is we did get G now, right? Let's see, maybe that was the fourth character. So I'm going to zoom out. Yeah, it wasn't the first character, it was the fourth character, which is fine. Because, again, after decoding, this would be F, L, A, G. So we got the correct interpretation, so it wasn't flipped after all, looking from this perspective. So this was okay. It was, oh, sorry, this was 2. And this was all zeros, which is 0. And 12 and 6, which is G. 12, 6. So this is fine. Yeah, the decoding is fine, and you can actually do it hand by hand, character by character. There aren't too many characters here. well, okay, there are some, so you probably don't want to do it by hand. So the way you could do it from now, and I guess I'm going to leave this as an exercise in hopes of saving some time for today's stream, is you should transcribe this schematic into an array in Python. You should transcribe this mapping into an array in Python, and then you should figure out if kr is 1, if this is 1, then what are the states of, if this is 0, like low, what are the states of all the scanning bits? And then go through the first mapping, look up in the matrix, in the keyboard matrix, what is the character, and that way you would get to the flag. So I'm going to actually leave this at this, because what's left is to do is the processing of a CVS, and that's actually easy even if you're a beginner. I'm just going to tell you that if you're looking for the schematics which I'm using, these are for Atari 800 XL with Freddy, so that's called XLF. Freddy, I think that's a kind of a memory chip, I'm not super sure about it, by this person. So do Google up these schematics, and that way you will be able to continue it from here. And yeah, what's left is only decoding. Now, there are a couple of important things. First of all, what's the case? Because we know that which key actually was pressed. But if we know which key was pressed, we don't know if it was a capital key or a lowercase key, like uppercase or lowercase. And on today's computers, you would assume it's lowercase. That being said, on Atari, the default casing was upper. So this is correct. It is a capital G. Unless like shift was held, it was a capital G. So the flag was all uppercase. Because on the old computers, that was normal. And it's not normal now. Now it's like the default is lowercase, right? So, okay, so someone says that I can press some magic here and something will happen with options. But I have no idea how to, seriously, I have no idea how to turn it into a binary number. Options. Bin. I don't know. Okay, I'm going to leave it to you. And again, you can just do it by processing the CSV file. Now, a couple of other notes about this task is that, or actually not about the task itself, but about this. So what is, I wanted to show you what is this, because this is not a default keyboard connection, and this actually goes to, let's switch to, this goes to this. This is actually a PCB. Yeah. Focus, 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 please. I think you can do it like this to grab the focus. Okay, well, that doesn't matter. This PCB doesn't do almost anything. It just shifts the logic from 5-volt logic to 3.3 point logic, because at the other part we have a Raspberry Pi. And the Raspberry Pi has my script on it, which actually emulates a keyboard. So I didn't actually type the password. I did emulate typing the password on the Raspberry Pi, because what I'm doing is I'm doing a side project just for fun from some time now on, because I'm not in a hurry, where I want to operate the Atari, the 8-bit computer, using VNC, for example, remotely. And the first step for this was emulating the keyboard, connecting with TCP on one side, and that's why we have Raspberry Pi there, and typing something, and then Raspberry Pi and the PCB emulates it by sending proper keyboard scanning matrix signals to Pocky in the end, right? So that's why you didn't have to care about the bouncing the keys. Now, the bouncing a key is that if you press a mechanical key and then you let it go, on like nanosecond level, it isn't clear. It isn't a clear cut that you have. Yeah. So it isn't like this, that press, and then suddenly let go. It's more like press, and then suddenly starting to bounce. And then it like goes up. Because there's still some connectivity, but not really, and so on and so on. So you didn't have to worry about this, because, again, I didn't press mechanical keys while making this challenge. It was actually emulated. And the precision of emulation was actually better than that. So I made this challenge a little easier because you didn't have to worry about filtering out the bouncing as well. That being said, you still had to worry about the noise on the signal. So yeah, that was what this task was about. And again, because it's a rather easy task, I'm going to leave finishing it to you. And we can get to the other tasks. Okay, so let's do a short break for questions, and then we are going to look at... let's do the reverse engineering one, I guess. Yeah, let's do back to basics, because I should be able to finish back to basics in 1 hour, and then next week I'm going to do better zip, because I'm not super sure I could do it in 1 hour. So yeah, better zip is basically based on this book, Serious Cryptography. I started reading it because I wanted to make a cool crypto challenge related to stream ciphers, and yeah, after reading a couple of pages of this book on the chapter on stream ciphers, I got an idea how to do it. So, but this next week. And yeah, we are going to do back to basics. But before we do that, let's do a couple of questions. So yeah, basically like 5-minute breaks. There are only 4 questions anyway. Okay, do you see the question? Yes, you do. What do you think about Linux on Windows subsystem? I think that question is actually asked every live stream. I used it once or twice. It's okay for testing some simple user mode applications for me. It doesn't work for my setup because I use kernel mode functions which are not there. Like Linux on Windows basically emulates the user space. It doesn't care about, you know, drivers and or kernel modules in the kernel. So I think it's pretty cool. I don't use it that much. Do you read the FRAC magazine? Who doesn't? If you don't know, FRAC is basically one of the oldest and probably the most awesome, most technical magazine about hacking. And all the classical, I think like the classical Aleph 1's article on buffer overflows was also published in FRAC. Yeah. The famous smashing the stack for fun and profit, which was, I think it's the most influential article about buffer overflow out there, and it was in the 96th edition, so years ago. Do check FRAC out. Sometimes it's still being released, by the way. Like there's a release from 2 years ago. Initially it was released in 85, so this is pretty old school stuff here. There are some amazing articles. I do suggest looking at it. FRAC is pretty cool. Here we go. Okay. How much do you read daily? If you're asking about technical stuff, then it depends. I do read a little, usually some, I would say like some article. Oh, thank you for the donation, Walter. Thank you. I do read, I guess, like a couple of papers. Papers as in academic / researchy papers which are published a week in security. Apart from that, I sometimes read some books, but I do not read a lot of technical books. Like this is basically one of the exceptions, which I am reading because it's really amazing. And actually, cryptography is something I'm acquiring more and more tastes for. Apart from that, I do read other stuff like fantasy books. I really like fantasy books, and I also like manga and so on. So I do read apart from that quite a lot, but not technical stuff. I also do reviews for like the Programista magazine in Poland. It's like a magazine for programmers, as the name implies, and I do reviews for that. Not too many, but I do review some articles which are then being published in some future issues. So I can add that to the technical stack, I guess. And I'm not mentioning documentation at work because that's a different thing. Is the situation where a user process triggers blue screen of death a security bug? Yes, in general, yes, unless the process has to have admin rights. If that, then no, because the admin can trigger a blue screen anyway, one way or the other. But if a normal low privilege user can trigger a blue screen of death, that is considered a security bug. Is it just a normal crash, a denial of service, or is it something else? That depends on the bug. That being said, like for example, a blue screen of death requiring a physical access isn't usually considered a security bug because you can, just punch the machine with a hammer anyway, right? If you have physical access to it. Did you ask Dragon Sector about solving times for my tasks? I did, but I don't think I got any answers. Yeah, so about the wired CSV, I got an answer from Impler who solved that task. That not too long, but the longest it took to find the proper key map for the keyboard matrix. And yeah, that's all the answers I got. Yeah, as you probably know, there is the WCTF in China starting tomorrow night. So my team is like on its way to China basically right now. How many years of experience do you have? Depending which kind of experience are you interested in. But basically I have around, I don't know, 12 years, 13 years of professional experience in security, and 1 year more of that in general in programming. And if you're asking also about like hobby programming, then that would be around 27, 28 years in total. Cool, so that was a break. Let's end the break and let's go back to the basics. Back to the basics was solved by 21 teams, so that's actually half of what wired CSV was solved. Yeah, as you can see. So I downloaded it, and it goes like this. You won't find any assembly in this challenge. Yeah, this is a reverse engineering challenge without any assembly. Only C64 basic. Once you get the password, the flag is CTF, and oh, by the way, I didn't say why you have to add this in both this challenge and the wired CSV, because you do have to add it. Because neither on Atari nor on Commodore 64 C64 there was these characters. There were no these characters on the keyboard, so I couldn't make a password which has this because there was no character like this. So that's why you had to add it manually. So there was a good excuse to not follow the flag format. But yeah, we usually, I think in all other challenges actually we did follow this, but yeah, since like the old 8-bit computers didn't have these characters, there was just no way for us to do that. Which isn't fully true, but we didn't want, to remap the keyboard because that would make things just more tricky without any real reason to do it. Okay, so we do need, the challenge has been tested on Vice emulator. Vice is a Commodore 64 emulator. It has been tested also by my colleague, big thanks to him, on a real C64. And so it does work on a real Commodore as well. Perfect. Wait. Oh, what's this? Oh, okay. Sweet. So I guess I can go to the download directory. And yeah, there's the PRG file, crack me PRG file. Here we go. Looks like this. I guess this is not really needed. And it's said to be basic, but it's binary. So what's up with that? That's the first question. But maybe we will get some basic in the end after all. I do need to start the emulator though, so let give me... This is Vice. Wait. I'm pretty sure I had Vice installed. Oh, I know, I had it installed, but I had it installed in the directory of one of my Polish live streams. Because I did a live stream of cracking, not cracking, of adding invulnerability, of adding like infinite lives and so on to a game called Commando on my Polish live stream. And I did need the emulator for that, so here we go. This is the emulator. Now, I'm going to set a speed limit. I'm going to remove the speed limit later on, but yeah. You just drag the PRG file here and it's loading it. Loading. And this is the crack me. And it asks us for the password. So we can give it a password, ASDF, and it says processing. It will take a while, and then it says that, oh yeah, well, not really. Okay, now question number 1 is why does it change the casing? That's funny when I zoom in. Okay, but this is the proper way it should look like. So yeah, this is basically how it looks like. We can now press the break key, I guess. Is there a break key here? How do I press the break key? On old Commodores, if the program wasn't basic, you can press the break key and then list the program. So we can try to do that. And I have absolutely no idea how to do it in the simulator. No, seriously, how do you do it? It's probably the most hardcore stuff in this. Vice, press, pause. Oh, maybe that was escape. Let's try escape. Yeah, escape. Okay, perfect. It wasn't the pause key in the end. So it broke in some line, and we can type list to actually list the program. And this is the program which is actually executing. And yeah, so we can, I guess, start from that, or we can actually rerun the program. Let's rerun it again. And this is the moment where I'm actually removing this. No, I guess I'm not removing the speed. When I remove the speed limit, it actually, the keyboard starts acting really, really weird. So I'm going to type it again. Okay. And it says it takes a while, but it actually doesn't. So let's break it here. Let's do this, and let's take a look at what's going on here. There are some pokes, blah, blah, blah. Doesn't really matter. Right, okay. And then it prints password, please. So this is what we like. This is basic, baby. This is how basic looks like. Then it prints processing, might take a while. Then it checks the length of whatever we gave. I guess there is input. Input is actually like in Python. It gets input into the $P variable, and it checks if the length of a $P variable is 30. So the password needs to be 30 characters. If it is 30, then it goes to 250, which is here. Otherwise, it does some pokes, blah, 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 and then it goes to 31337. 31337 is actually here, and it says verdict, nope. And it goes here, and this is an infinite loop. So yeah, if we don't get the password right, we need to reboot because it goes into an infinite loop. So we know the password is 30 characters. Okay, so where is the checking of what is the actual password? So let's assume that we actually go to 250. We go here, then there's some poke, and there's rem is remark for a comment. This is the same as in .bat files in Windows. So the remark here is that never gonna give you up, haha, very funny. and then it does another poke, and it go to is just a jump, goes to this line again, so this is just another infinite loop. So where's the checking? How do we get verdict to say yes? It's not here. I don't know. Well, I actually don't know. But let's do this again. And let's enter 30 characters now once it loads. I forgot you, didn't I? I forgot V as well. So this is 26 characters. Yeah, so this is 26 characters, ASDF. Okay. ASDF again, and this is 30 characters. Okay, processing, and this might take a while. And it seems to be stuck. It's not stuck, it actually takes a while. It takes 18 minutes to finish it. And not because of calculations, but because how slow BASIC is. It's remarkable how slow is it. The computer isn't this slow. It's the BASIC. Like if you write something in assembly, it's way faster. It's like thousands of times faster. But BASIC is slow, and this application is in BASIC. So, but that's great, because now we can actually press escape and list the program again. So let's see if there's more. Okay, it seems it is more, and it seems that we have line number 2000 repeating and saying never gonna give you up. So for some reason, the listing of BASIC program got stuck there. So what's the deal with that? And yeah, this is basically where the challenge actually begins. And let's leave it here. And I am just going to show you how to deal with the speed, which isn't really hard, I guess. Okay. Okay, so this is 30 characters. No, it's not 30 characters. Let's try it again. But basically what you do is you change the speed, and it takes way faster. It's way faster. Oh, now I got it. Okay, 20. Okay, 30. Okay, it's processing. You basically go to maximum speed and no limit. And now it's faster. It still takes several seconds, but it's way faster. That's because my computer is slow, I guess. So let's go back to the PRG file again. Now, while solving this challenge, you would have to look at the documentation for the PRG file. What is the PRG file? How is it structured? Actually, the structure of a PRG file is trivial. And I mean trivial. It's like has header of 2 bytes and that's it. And that header, let's let it finish. But it will say, as you can see, there are no green hearts here. So it says nope. Maybe we got the end right though. Because it says, yeah, that's a green heart. That's something. That's a win. Yeah, so the header is basically this. And if we look at it like this, the header basically tells it where to load the rest of the file, where in memory to place the rest of the file, and the address here is 801. So this is the address, right? And then you have the rest of the file. Now, let's look at some... we can close this for the time being. Let's look on some C64 Wikipedia for memory map. And like the old computers, they're usually really well documented, so you can find them. And the address is here, and it says free basic program. And this is this page. Let's go here. And let's see if there's some more information here about what's this. I guess there isn't. but there are resources. I'm not going to go right now into digging into the resources of it, but I am going to tell you what's under this address, because you can find it easily. So under this address is actually the basic program, and this is pretty standard way to do it. You load the basic program into memory. So yeah, everything here, all the binary looking data here is actually the basic program. But why does it look binary? Like, well, this doesn't look binary, right? But we don't see any print. Where is the print? We saw prints, right? Like, for example, here we saw prints. Where is the print? Where is the input? It's not here. Why? Because this is actually compressed. And to be more funny, it's actually dictionary compressed in a really trivial way. All the bytes which are higher than 80, higher or equal than 80, so have the most significant bit set, are entries in the dictionary. And the dictionary is constant, is like pre-programmed. So the things which are in the dictionary are actually basic commands. So all the basic commands like print, like input, like if, like data, and like go to are expressed by these high bytes, like 99, for example, or D3. So you do have to find a dictionary of these, and I don't know how to do it. I guess we have to Google for it. C64 basic dictionary, like command map, command list. Oh, here we go. Okay, and let's look at a random one like print. Where's print? I don't see it. Here we go. Okay, and here we have a token or the code. So 99 is actually it. If we go to this page, we have all the... This is the dictionary, the compression dictionary, basically. So if we again look at 99 here, this was actually a print followed by something. So this was, yeah, sorry, here it was a print followed by something, and this is probably actually the colon is like next line. It's not next line. If you want to squeeze several commands in one line, then you had to use a colon. It's like a semicolon in C. So yeah, that's basically how this file is structured, and you can use tools from Vice, for example, to list this file. And there is a tool called, sorry, let me open the console. Okay. Petcat. And petcat is the file which actually understands this and can print, can decompress it for you. So yeah. And yeah, and it prints and decompresses, as you can see. This is where it's supposed to load, and then it decompresses it line by line, like, or actually character by character. And as you can see, it stops here, which is quite weird, because how much output is this anyway? So let me put it in this file, which is magnificently named, and let's do an ls. And as you can see, the file, the output is just like 2 kilobytes, under 2 kilobytes, and the PRG file is like 32 kilobytes, which basically tells you all you need to know, that some of the input is hidden away. It's executed, but it's hidden away, so you'll have to find out why. Now, if you start going deeper into the format of the basic, not of the PRG file, but of the basic interpreter, how things are stored in memory, you will find out a couple of things. First of all, you will find out that it's actually a linked list. So we do see lines, and each line has a number, right? And this is great, because if you're programming on this machine, it doesn't have like a modern editor. The way you programmed at the old machines, you set line number and then what's supposed to be in that line, for example, this. And if you wanted to change that line to something else, you typed the number of that line again and changed it to something else. So yeah, that's basically how editing worked at that time. So you could obviously do this, like, for example, now I want to add a line number 20, so I just go up, change it to 20, press enter, and it reparses the line where my cursor was at. So yeah, there are line numbers, but actually you do not use lines like 1, 2, 3, 4, 5, because what if you want to squeeze one line between two, like you had line number 1 and line number 2, and now you want to add something there. Well, there was no easy way to do it, so people actually didn't use 1, 2, 3, they used 10, 20, 30 and so on to always leave at least some space between the lines so you could add another line later on. And also, if you had like parts of a program which you wanted to logically separate, you would do larger jumps, like for example by 100. Here you do a jump by 100, right? So I was at 90 and then I decided the following lines are actually doing something different. So it was, I jumped by 100 and then I said, yeah, this code is doing even something more different, totally different. So I started coding at 2000 and then I jumped to like this line. So storing it in an array would actually use all of that computer's memory. Now, if you do know your Commodore 64, you know that 64 is actually also the number of kilobytes of memory that you had. So you had only 64 kilobytes of memory in C64. So if you do an array of lines, you basically just waste all your memory for indexing, basically, not even the lines, just indexing. So it couldn't be a line. Now, what we would do now, probably we would do some magical tree-like structure or hash-based structure. But what they did, and why would we do that? We would do that because Goto takes the line number as input, and we do have to translate it runtime to to the actual place where the line is in memory, right? And using a tree-like structure for that is really fast. But, well, it's not the case in C64. That's actually a linked list. So we have a linked list of lines. So let's go here. That means that, for example, if we have line number 10, what we do have stored in the list is the number 10. Then there is the line, the text. And also at the beginning of this entry, we could have either the size of a line, but we don't have that. What we have is we have a pointer to the next line. So let's assume that the next line is somewhere here. So 20. And this is another line. Like a typical linked list, a single linked list, single pointer linked list. So yeah, if line 30 is somewhere here, then we have another pointer to it, and so on and so forth. So if we wanted to inject now a line number, for example 15, what would happen is like somewhere in memory we would get the line number 15 with some text, and this would stop pointing here and instead point to line number 15, and line number 15 would point to line number 20. So it's actually pretty efficient for editing that way, right? Because the lines don't have to be one after another in memory, you just have to have this linked list. And what we have in the PRG file is actually this linked list of lines, right? So that means that here at the beginning of the line, we do have the address of the next line, and that's actually, this is little endian, so that's 81E. So if we look at, and do remember that this here begins at this offset, so this is 801. So yeah, this means that if we go to 1F, so we remove the 8 and we add actually 1 at the beginning, in the file, which is here, this is the start of the second line. What is the next stuff here? Like what is this, for example, right? This is the line number, if I'm not mistaken, and we can check that in a second. But I think this is the line number. Then we get the actual line content. So this is the line content. And the line content is ended with a null byte. And then we again get the pointer to the next line. So this is the pointer from the linked list here. Then the number of that line. And then, so this is 2. So I guess like the first lines are like 1, 2, and so on. And then we jump further back. And the content of the line terminated by a 0. Again, the pointer, number of the line, content of the line terminated by 0. This is line number 10. So it should be line 1, 2, 3, and then line number 10. And let's see here if that's actually true. Yeah, we have line 1, 2, 3, and line number 10. Now, We have some, now let's look at this code, what's going on here actually. We have some data. Data you can ignore. Like, what it does is actually like an array with constant variables, and there is this read command which actually reads them. But this here is only for displaying the logo, the back to the basics art, which is there, so we can totally ignore it. The more interesting instructions are actually pokes. So these pokes here, if you would look in the Wikipedia, it's in the screen memory, and that actually changes the color. So this is changing the color for the art, that doesn't really matter. What matters is what does the poke instruction does. And you probably know, if you watched any of my return-oriented programming live streams, because I do like to use the poke instruction. Poke means write to memory. So and this is pretty standard for basic. Poke is write to memory. It's like memcopy a variable, basically. And then there is the second one, which is peek, and this is read from memory. And this is write a byte to a given memory address and read a byte from a memory address. So this means write to this memory address, this is decimal, and this is the value of a byte. And this is write something else, and this is why this could be used to a couple of things. Well, first of all, to modify memory, but second of all, if there was some memory mapped I/O, so communicating with some other parts of the motherboard, or like the computer, the graphic chip and so on, or the sound chip, would have addresses in memory which they would look at, or would actually, these addresses would be mapped into the given device. And by manipulating the memory, would actually communicate with that device, would, for example, start playing music or do something, right? Here, what is the important pokes and peeks is this part, this line. This is the key line in this. Because as you can see, it actually does something with this address. Now, this address isn't octal. The 0 here is for reasons. If that fooled somebody and somebody thought that's octal, that's amazing, and I actually like it. But let's see that address in hexadecimal, and that's actually D45. Now, D45, if you start thinking about it, it's surprisingly close to this 801, which is the basic memory, because our file is like huge. So the D45 is actually falls into the basic program. And given that we don't see the full program here because something, what you might figure out, or actually, find it in the file. Let's find it in the file. So that we have to subtract this, but add 2. So this is the offset in the file. 4, 5, it's somewhere here. It's almost the top of the file. 6. Okay, it's this line. It's the line never gonna give you up, which we saw before, right? It's the line with the remark. So if we look here, it's actually this line. Actually, it's not the content of the line, it's not the number of the line, it's the linked list pointer. So this is modifying the linked list pointer. It says, okay, this line from now on at runtime should actually point to a different line which is not displayed here. Because here we see, a dead file, and the dead file, the linked list is pointing to this line, but then at runtime we actually change it to some different content somewhere else in the file. So this tricks the basic interpreter, because it is a basic interpreter. Basic is not a compiled language, it's a true interpreter. Will go after executing the goto, will actually not go to this line, but it will find this line, and then it will go somewhere else, and somewhere else in memory there is probably some other program. So what we could do here is we can grab the file with a hex editor and actually, change it, like in the file, and see what happens. So I'm open this file. We did calculate the offset already, which is here. So let's go here. Control G. Yeah, this is the offset, and we have Intel set. So we see, this is the, I guess, the value, which is the original address. Now, what do we change it to? We change it to 199, and this is, again, this is not octal. This is decimal, so 199, and the other one is 13. So this is lower and higher. So we change it to D C7D. Here. C7OD. So this isn't far enough. This isn't far at all. Okay, and now let's run the PETSCI again. Did it work? Or did I actually manipulate the copy? Sorry. Okay, yeah, it's... No, it's fine. But it didn't seem to work. Why didn't it work? So we changed that. Oh, I probably know why it didn't work. It didn't work because PETSCI actually what it does, it doesn't follow the linked list. It just like brutally reads the file line by line. We have to run the real basic for that, so let's do just that. So let's run this, let's load the application and press escape. No, I want to press escape. Okay, and now type list. Okay, and did it work? No, it didn't. So, I don't know why. It should actually have worked. Okay, never mind. I'm going to change it in runtime then. I'm going to do a break at this line. Yeah, here. I'm going to change this to stop, I think is the command. Not steep, stop. So, yeah. Okay. Now I'm going to run it. Okay, loading. It should ask me for the password. I should be able to give it the password, and the password does need to be 30 characters. So... Okay, yeah, and it broke. And after modifying the linked list, I hope, so we can do list now, and it should work. Okay, it does work. Perfect. So what do we see here? Now we see that this never gonna give you up. Actually, there is some other code after it. Like there is some other pokes, I guess. And this pokes does something. What does it do? And there's some binary garbage, by the way, which is also funny, which means that maybe I didn't modify it correctly. You know what? I'm going to do one more thing. I'm not going to close it. I'm going to read the program from a copy. I'm going to repeat it because I did use my modified. Maybe I modified it wrong or it miscalculated the offset or something. Why don't you want to break? Again, but this time please break. Okay, and again changing this to stop. Okay. I'm going to list it just to be sure that my stop is there. Well, it was there. Okay. So I guess I can continue, I think. Continue. Can continue, so yeah, run, whatever. I wonder if I can just copy paste several characters. That would be way more useful. Edit, paste, okay. Okay, now let's check the list. Well, it doesn't change, it didn't change anything, which is funny. Yeah, it seems my obfuscation is actually better than I expected. That's cool. So what should happen actually is it should go to a different set of lines, and I am going to do I guess I am going to try to repair it once again because I really want you to show it to you. And to do that, I'm going to. So I did the modification here, and I'm pretty sure this modification is cool. And at the end of this line, I'm going to start commenting stuff out, probably. Or I'm actually going to make this line super huge. To go, where is this offset again in the file? Let's calculate the offset in the file. Is OD C7. I'm going to subtract the 081 and I'm going to add 2. This should give me the offset in the file. 5C8. So 5C8 here. Give or take. Yeah, this is exactly where. So I'm going to change everything here up to that point with ace, because not this kind of ace. Okay. Okay, and let's see if this works, because this should work. Okay, perfect. Pesky actually crashed and the debugger appeared. But that's fine. Yes, this worked. Perfect, finally. Because we have this. This is the new code which I was looking for all the time. As you can see, we have some variables being assigned. And a funny note about variables in C64, because you can see these variables are like 2 letters, this is a 4-letter variable, a 6-letter variable, and so on. Now, in C64, only 2 first letters count. So it doesn't matter if I would type like ASDF or ASER, it's the same variable. I didn't use that in this CrzaQ. I might use it in some mission in the future, who knows, but that's the case. Only 2 first letters count. Furthermore, there are only, I think, 3 or 4 types of variables in BASIC. It's the Boolean type, the integer type, and the float type. And the default type of the variable and the string type, obviously. I don't think there's a Boolean type, by the way. So scratch that, no Boolean type. So only 3. Anyway, the funny thing here is that the default type is floats. So it's same as like in JavaScript. The type number in JavaScript is just floats. Here it's also floats. So yeah, all these like ES, EE, and EK, these are floats. These are not integers. Integers have a different I think they have like a hash at the end or at the beginning. I don't remember. I think at the end. Anyway, so yeah, so we set these variables to something, and then we go for a loop. This is the loop. Now what this loop does, it actually grabs some memory from I being this, and this is again the program memory range, right? This is where the program is loaded. Lucky guess, it's actually here. Then it grabs the memory from there and adds something EK to it, and actually ends it with 256 to always get a byte. So this might be decryption of a code, decrypting this code here. So let's try to actually apply this decryption to the code using a hex editor, assuming we start at this address, we end at this address, and we are using this as the key. To do that, I'm going to use a Python script. So go.py. Okay. Now I do need to load the CrzaQ into my script. So, oh sorry, let's make the font a little bigger. Open this, read binary, read it, and I have a byte array. Perfect. Now, what are the? I guess I can just copy this line, like almost without changes. But yeah, this is not octal again, this is decimal. So this is fine. What I want to do to that file, and let me change the name of, create an output file as well. The output file is going to be CrzaQ2 with masakra b. Okay. So what I need is an offset in the file, and the offset is again minus this address plus 2. This is the I will use to calculate the offset in the file, and I'll do the same loop. I don't remember if the last address is also taken. Is it inclusive? I think it is inclusive. So for I in range, or X range actually, ES 2EE plus 1. I think it's plus 1. I think it's inclusive. We do D of offset plus I. We add to it EK, the key. And byte array will actually do the AND 256 for me. It will make sure that this is a byte, I hope. So you can run it, go. No, it doesn't do it. Yeah. So I do have to do it manually. Here we go. Okay, and let's see if this gave us anything. And it did. We have this code, which has been decrypted. So let's see what's happening here. You might remember that $P is actually the password variable, the variable which contains our password, whatever we have written into, right, our input. Mid is actually substring, and I think there are some other languages which use mid, but yeah, this basically gets a substring at index 1 and the length of 1, and then to variable bb it gets a substring from password from index 2. Basic is 1 index, it's not 0 index as C is or Python is, it's 1 index, like starting from 1, like is Pascal, for example. And yeah, and you get 1 as well. And ASC is actually ORed in our modern times, which is, it grabs the ASCII number of that given character. So yeah, BA is the first character, the code of, actually not ASCII, the PETSCII, but that doesn't matter, of the first character, and BB is the second character. Then we have quite a lot of variables which are being zeroed here. Yeah, quite a lot of them. 12 of them actually. And then we have this thing, like quite a lot of ifs, right? So let's see. It takes the first character and ends it with 1. So it selects the first bit, the least significant bit of the character. And I guess if this is true, like the bit is set, then it sets P0 to this number, whatever this is. This looks scary, and this is totally a floating number. Yeah, so it's either 0 if the bit is not set, and if the bit is set, then it sets P0 to this. So yeah, this is basically like just the bit number, and it goes like with all the next bits. This is the second bit, the third bit, the fourth bit, the fifth bit, and so on and so forth. Up to, well, here it changes to the second byte, and it gets, I think, 13 in total bits. And what does it do with these variables after it sets them? Well, it actually adds them. So it has some v, which is some initial value, and it adds everything. So these variables are either these strange numbers here, or are zeros, right? And it adds them together, and then it has some g. Well, what is v, by the way? V is, again, some weird floating number minus some other weird floating number. Perfect. And the g is set to some other floating point number, and then it does T0 k equals g. So it checks if these things match, and it returns 0, or in case of true, it returns -1. So it's same like Pascal, it returns -1 and not 1. In modern languages, it's usually 1, and if you cast a boolean true to integer. Here it's actually -1, because reasons. Then something. So if t is -1, so if this is true, if it did match, then it changes a to something and b to something else. And then it pokes somewhere, like writes some memory, 90, and then does again decrypting or encrypting something, and again messes with the linked list of a program. So what we can expect, because here only 13 bits have been tested of a password, what we can expect is that there are more of these blocks testing other parts of a password. If you remember, the processing thing actually had quite a lot of places to where it said it's checking the password. And since we don't see any loop here, we can assume that each character in that processing progress bar is actually one block like this, which gets decrypted at the beginning. Then the processing is done, and then it gets encrypted again, and the linked list is being switched to the next block, which gets decrypted. Processing is done, and then encrypted again. So at no point in memory all the blocks are decrypted, so we would have to handle that. Now, One more thing which I wanted to add here. So I wanted to add something, but what did I want to add? Okay. Yeah, about the floats, because there's a lot of float manipulation here, and in the end, what's actually being done is float equals to float. If you're a programmer, which actually does quite a lot of programming, and you're quite senior, you know that you never use the equality operator with floats, because that's asking for trouble. And here I'm using the equality operator for floats, so what's up with that? So this is, yeah, another part of a challenge, and I'm not going to go decrypting all the other blocks because they look identical. They just select next character and the numbers might be a little different, but I'm going to focus on this block. What's up with the floats? Now, first important piece of information. On our modern computers, we are using so-called IEEE 754 floats, or actually even the newer version, but this is the name of a standard which defines how the floating point numbers work on the, and this standard is implemented on the processors, on the floating point unit in the CPU, and we basically and like also in the GPU, right? And in the CPU we have three in Intel types of floating points. We have 32 so-called single precision floating points, 64 double precision floating points, and this is an Intel extension which is kind of weird, kind of funny. I really like it. It's a little slightly different, not really different, but slightly different due to something. But this isn't about floats on Intel today, so I will not go over. It's either called long double precision or it's called like extended precision, I think. Doesn't matter. Now, on the C64, the CPU didn't have any floats, but BASIC actually implemented floats in software, and the floats are, let me try to do the quick math, 40 bits. They are 40 bits, so they are neither of these, and they do not follow the IEEE 754 specification. These are different floats. They behave more or less the same, but the math on C64, the float math, works differently than it works on our modern computers. And this is an important thing here, because what I did in this challenge is I made the math work the way that it's not possible to directly just copy-paste the code and run it on x86, because on x86 it will give different results. I specifically created the math which is done here, so it behaves like this. So it cannot be directly used on x86. That's not a huge problem. You can still do approximations, and most of the teams which solve it did approximations, and that's fine. And it wasn't supposed to be too hard. So what are these numbers? Because these numbers look scary. Let's look at this number. It looks scary. I'm going to copy it. And now I'm going to put it in Python. It didn't copy. Why it didn't copy? Please copy. Thank you. And in Python, what you can do is you can actually dump a float in hexadecimal. So let's do just that. And as you can see, the number in hexadecimal doesn't look that scary at all. There's a 1 here, some zeros here, a 2 here, and some zeros here, and something. This means that only 2 bits are set in this number. This bit, which is here, and this bit, which is here. Now, each digit here represents actually 4 bits, right? It's a standard hex nibble, a standard hex digits, which is 4 bits. So if we start calculating how many bits are between the 1 here and the 2 here, it's 1, 2, 3, 4, 5, 6, 7, 8. It's 8 nibbles. So I said 8 times 4, that's actually 8 times 4, that's 32. Now, I did say that the Commodore floats are 40 bits, right? But floats are usually divided into 3 fields. The first field is actually the sign, so as you know, minus or plus, right? The second is the so-called exponent. N is usually the smaller field, and the third one is I think it's called the mantissa or something like that. There are a couple of names for it. Let's use mantissa for that. Now, this is the largest part. I think in Commodore 64 it's something like that. This is 32. This is 32. This is 7 bits. And this is, well, 1 bit, because for the sign you need only 1 bit. Now, what is what? Exponenta basically is the field which says where the dot is placed. Where is it placed, right? So if we have a number like 1, 2, 3, the exponenta can say, yeah, place the dot here, or it can say, no, actually place the dot here. Or it could say place the dot here, like, and add zeros. And this is why it's called a floating point, because the exponenta floats the point around, right? So you have a set of digits, and the digits, which are here, are actually in the mantissa. And then the exponenta says where the dot is supposed to be in this set of digits. So this is how floating point works. That's actually exactly how it works, by the way. So, while our mantissa is 32 bits, and this means that actually this from here to here is already 32 bits. So the 2 here, it cannot fit in a 40-bit float, which is true. It will fit in a 64-bit float though. So given that it's going to fit in a 64-bit float, that's why on modern computers the math is kind of broken, because I've chosen a number which is interpreted differently on a modern computer than it was on C64. So we can ignore it, because only this part will fit on C64. And this is just 1 bit set. So let's look at another number. Let's look at this number here at the end. And let's do the hex on it again. And hey, guess what? This is also only 1 bit set, but a different bit. Like, this is the exponenta, by the way, here, the -4 or -28. It says where the dot is placed again, right? So yeah, just imagine that this dot isn't here, is like 28 characters that way, that direction, 28 bits that direction. And yeah, if you look at all these numbers are actually just 2 bits set. Then, so each of this number is a bit set, and this would be, this would be bit number 4 here, at the first number that was bit number 4 was set. Here bit number 6 was set, like in the second one, in the third one bit number 8, and so on and so on. So you'd see that's basically just setting a bit on a given position. And then you add the bits together. And you add the bits to actually the V, whatever the V was. Now the V was something like this. Let's look at what is it. So, no, it didn't copy again. Come on, please copy. Why doesn't it copy? Or does it just paste the result? Well, it doesn't matter. I'm going to copy just this. The other number doesn't matter for what I want to show you. Yeah, if you look at it, and actually I'm going to grab this and I'm going to do a binary dump of this. It's this kind of a bit pattern. So it's just 1 0 1 0 1 0 1 0. And what is happening with all the other bits being added to this number, it actually just sets one of these bits, like sets this bit, for example, sets this bit, sets this bit, and then sets this bit, for example, right? And when these bits are set, it starts to compare it with this number. What is this number? Let's copy it. Let's dump it in hexadecimal. And let's again copy the mantis and dump it in binary. The mantissa, yeah. And it's actually this, you can ignore it around here because the precision isn't enough. But you can see that this is again the same pattern with 1 0 1 0 1 0, but only now some bits are actually being set here. So what this all math is doing is just copying bits from the password, from the characters of the passwords into this number, into the specific positions, and into this pattern of 1 0 1 0 1 0. And then it compares the two patterns. So if you actually grab this number, grab this pattern, and extract all the bits here, you get the characters of the password. And And yeah, this is basically what the challenge is about. You can either do that, you can either take the number, like the G number from the source code, from all of these blocks, and grab the bits and extract them and put them into characters, and then you get the password, right? So this is one way you can do it. The other way you can do it, which I guess most of the teams did, is just copy the math and do approximations, brute forcing it. Because if you look at the math, you only take into account 13 bits. That means that, well, you have 13 bits to brute force. What's 13 bits? It's like 8,000. 8,000 possibilities, that's nothing for brute forcing, right? For each block, there are, I think, like 20 of these blocks. You do brute force 8,000. So that's, yeah, that's nothing. So you can do it, brute force it like this, and do the approximation of this number on modern computers. It won't be exactly like this, but it will be close enough. And then from that, you can derive the bits and concatenate the bits together and read the password, which then you enter to the there. Okay, so this is basically what the task was about. If you are curious and you want to finish it, then by all means. Otherwise, we can try to enter the flag, and which we would derive after what I just described. So let's do just that. Okay. If I remember the password, let's see if I remember the password. So the password, if I remember it correctly, was linked lists and 40-bit floats. And yeah, that's 30 characters. So that doesn't work too well. Sorry. Selection, how do I do edit case, convert case, lower, okay. Edit paste, yeah, this is fine now. Okay, and it's processing, but I'm going to speed it up with, sorry, that would be too slow, no limit. Okay, and as you can see, it's actually, this is working. So this is what you would get after you would decrypt all the blocks, get the math out, and yeah, and finish, and either get the bits from this floating point number, or without looking into the floating point numbers at all, just approximate this math and get the closest result you can get by brute forcing all the bits. So that was this task. Now I am going to, let's go to the open source directory, because I wanted to show you how the task is actually made inside. So that was Quals, that was basics, yeah, and source code. I actually had to create, and sorry, where is it? A basic compiler just to do that. The basic compiler is terrible, and yeah, it's a nasty hack of a basic compiler. I'm sorry. And again, it's not compiling really. It's kind of like more like pre-processing and then compressing it to the dictionary compressed form. So it generates the PRG file. And I added a few features. One of the features is like that I can, instead of entering a number, hard coding an address in memory, what I could do is I could say, yeah, grab the address of this line and put it in this poke. So that's one thing. The other thing, I could have encryption, so like sections which are encrypted with this algorithm. I will show you the source code of the CrzaQ in a second. And I added like hexadecimal numbers and a couple of other things which I found useful. Let's go to the source code of the actual challenge. And this is the source code of the actual challenge. Yeah, as you can see, this normally wouldn't work on C64 because this is hexadecimal. This is notation from CPC 464, which is an Amstrad, another computer, and they in BASIC actually had a hex, so that's why I used this character. Anyway, this is, by the way, if you didn't know, this is a print, like a short form of writing a print. yeah, never gonna give you up. And this is like, here I slash the list. So this ends the list, the linked list. And here is the line which actually reattaches the list runtime. As you can see, I'm using the macros, which I did describe in a second. And then if we go here, there are the checkers, and the checkers are very actually submitted. I think the checkers are, please tell me they are submitted. They're not submitted. That doesn't matter, because we have part of them somewhere here. Extract first, no. I will show you this in a second. Genprog, yeah. This is the program in Python which generates the checkers. And yeah, I have labels for some reasons. I do encrypted sections, and this is the encrypted section. And this is some templating which I'm using. This is not a feature of my compiler. This is just Python templating. And yeah, this is how it basically works. So feel free to do analyze the source code. You might learn something. Extract vars is a tool which I've written, which you basically give it Vice snapshot of a program, and what it does, it goes through basics memory and dumps all the variables and their state. And this was pretty useful while debugging. So I guess I can show you how it works, because and then we can, I guess, start to finish the live stream. Okay. Okay, do I have Vice still opened? I have it opened, perfect. So, sorry, I'm going to move it here, snapshot, save snapshot. Okay, so I've saved the snapshot at this point. I'm going to close it. This is the snapshot. The snapshot has something which I totally ignored. And apart from that, this is just raw memory of the RAM. And let's run it. Python extract vars and then dump. Yeah. And these are all the variables which are in memory, which is again the string. This is the string, and then all the variables are floats. And I'm actually printing them in binary form because I needed to be sure that the float math is exact, is bit perfect, right? So this is why I'm printing them in binary. This is the mantis, the sign, and this is the exponent, and this is plus minus the value, like circa the value in modern math, in modern floats. So yeah, that's about it for this challenge, I guess. And do take a look at the source code if you're interested. Again, well, not all, but most of the challenges of our CTF have been already open sourced. So I guess that's going to be it for today. I am going to answer some questions, and then we'll finish it up. Next week I'm going to talk about the last one, Better Zip, which is crypto. And yeah, if you wanted an excuse to learn Commodore Basic, then I guess this is your chance. Let's go with the questions. Okay, I stumbled upon this code, and that's a standard buffer overflow on Protostar Ubuntu 32-bit. So I did the usual knob shellcode pointer, okay, pointer to middle of knob. Yeah, that's the standard way you do it. You do a knob sled, and then the shellcode. When I looked into memory and my shellcode was all of a sudden corrupted. Now, is that a 32-bit thingy, or am I just dumb? Well, first of all, you'd have to assume that that the memory is actually executable, that the stack is executable, because that's what where you're placing your shellcode. I'm pretty sure that was the case, that stack was executable in this challenge. Now, the second thing is gets actually if it finds a new line, then it will stop reading the data. So we need to take that into account, that if you But yeah, if your challenge for some reason has a new line anywhere, like, you know, the binary form of your shellcode contains a new line character, then gets will stop reading. So be sure that your shellcode doesn't contain any new lines. The good news here is that actually somewhere in memory you will find in the memory of it's actually mmap memory, somewhere mmapped in the memory by libc. You will find the standard input buffer of libc, and then your shellcode should be fine, just fine with all the binary characters. You really rarely need that in exploitation, but it is there in memory. Apart from that, there's one more thing, mainly when exiting the function, after gets, there's a return, right? And, well, it's not in this code, but usually there should be a return. There might be some additional code added by the compiler, which is changing the stack. Like, I don't know, just restoring some variables, because why not, right? And that's why you don't usually look at the source code, you look at the binary, because the binary is the ultimate truth, basically, for exploitation. You always look at the binary, you never look at the source code. Well, you look at the source code to understand the binary, but when exploiting, you do look at the binary. And yeah, that's, I guess, about it. I'm not sure about nulls, like null bytes, like 0 bytes in gets. I think gets actually handles them fine and reads them fine, but do check if that's not a problem too. And I think that's actually it. I mean, my take is that if it didn't work, that was because you had a new line character somewhere in your shellcode, or in the address which you overwritten it with, or a null byte in case of gets not handling it. But I'm somewhat sure that gets actually does read the null bytes as well. It doesn't complain about null bytes, but don't quote me on that. Do check it. 16-bit, so we have words by 2 bytes, I assume. I guess that's the question about the challenge, but I'm not sure about which part of what I did discuss is this about, so I'm not sure I can answer it. But yeah, 16 bits means 2 bytes usually. What do you think about Troy Hand hebi API for verification if your password is not leaked in public database dumps? I have no idea how that works, in all honesty, so I don't know. You can, I guess you can do it correctly and you can do it incorrectly, right? As in, I'm pretty sure you don't send them the password to verify it. It's more probable that you send them a hash of a password. If you have a strong password, that shouldn't matter. A hash of a strong password should be fine. Like, I mean, really strong, not brute forceable password. If it works, it could also use some more magical crypto, which, even without disclosing information, you could verify that something is in the database, because yeah, that also could be possible. But yeah, I'm not sure how it works, so I cannot answer the question. I'm sorry. I wonder if you could brute force this challenge using the hearts. So each heart is per 13 bits, and 13 bits is 8k, which means and that's actually less because you get only printable characters. So the answer is yeah, totally. Yeah, you could do it. You would have to instrument Vice or something, but that's totally a valid solution. How would you go about figuring out that the C64 use 40-bit floats? They actually, on the C64 Wikipedia, it's actually written there. Like, the basic is described really well. It didn't... I think it has almost all the information you need to solve this challenge, with 1 or 2 minor bits missing of information which are quite easy to figure out. So yeah, you just read it on Wikipedia, like, basically for that computer, but yeah, it has 40-bit floats. And that at that time was pretty normal. That like most of the 8-bit computers from that era actually had 40-bit floats, or like close to that, which were pretty similar. So you Google it up as the answer, basically. Okay, Not Wearing Pants says that he wrote a backup for wrote a write-up for it, which I'm going to give you a link for. Okay, so yeah, there is. Oh, I did read this write-up. This write-up is amazing. You like, if you're not going to solve the challenge, or even if you are going to solve the challenge, do check out this write-up. I had quite a lot of fun reading it. Yeah, after, you know, doing a challenge, you usually Google for write-ups. Okay, their best supervisor says, no new line. I execute it into the knobs and slide it into the now corrupted code. It's a good question, then start debugging. Again, it's the second thing, as in maybe the compiler actually mixes the stack due to some reason. Check it. Maybe that was the case. But without looking at the binary, it's hard to say. But the answer is in the binary. Something must be happening to the stack, or there is some character which basically breaks gets, and gets doesn't read the full shellcode. It's probably one of the two. I wouldn't expect anything else, seriously. When you do nmap scan, they can figure the service version depending on what was called fingerprinting. How does it work? I think it depends on the operating system. So, okay, it's a good question. Yeah, basically, it works on, like, fingerprinting the version can work on a couple of levels. And first is direct. Basically, if the service says, hello, I am, like, Apache 2.4, then that's probably Apache 2.4. And that's pretty direct, pretty obvious. I guess that's not what the question is about. What if the banner is actually hidden, or the banner is like never there? You can try to derive the version from minor things. Like, for example, in case of HTTP, what is the order of the fields which you are, like, of the headers, HTTP headers, which we are getting back? What is the exact structure of it? And usually some such small things are pretty easy to fingerprint the server, or like the framework or whatever. Or maybe like content type, the type is written with a lower t for some reason, and that's only happening in this family of servers, right? So this is usually it. And in case of lower protocols, is you look at the flags, like, for example, TCP or IP, right? Or at the values of some fields, because, for example, if you ping something, right, then the TTL, time to live, on Windows is set to, I think, 64, and on Linux to 32, or the other way around. But it's actually different on the operating systems. So you look at that, you look at on some other things, you look how it behaves, and you can usually fingerprint the version. Not to the, like, exact number of the commit, but at least to the family, or to the family of what kind of software is this, or to the major version. Sometimes, if you're super lucky, to the minor version, if there was a huge change in how it behaves. But that's about it. Okay, and that was all. So thank you for today. Do try to solve by yourself the tasks which I just shown, or any other tasks from Google CTF. And see you next week, where I'm going to talk about better zip. So yeah, that's it. Thank you to Foxtrot Charlie for being the moderator today. And have a great evening and happy hacking. So yeah, see you next time.